My name is Zane Mills,
And I'm Connor Olson.
and for our video, we're going to do problem 69 from chapter 1. It's a problem compiling a lot of equations from chapter 1, and it goes, in a recent suspense film, two secret agents must penetrate a criminal stronghold monitored by a lithium photomultiplier cell that is continually bathed in a light from a laser. If the beam of light is broken, then an alarm sounds. The agents want to use a handheld laser to illuminate the cell while they pass in front of it. They have two lasers, a high-intensity red ruby laser and a low-intensity violet GAN laser, but they disagree on which laser would be better. Determine which laser they should use.
Alright, so some of the important numbers that are given in this problem are the wavelength of the red light and the wavelength of the violet laser, which are, could you read me through?
Yeah. The wavelength of the ruby red laser is 694 nanometers, and of the GAN laser is 405 nanometers.
And then there's also the work function of the lithium plate, which is, could you say?
2.93.
Alright, so the way this problem works is that we want to make sure that the laser shining a beam on the lithium plate is always stronger than the work function of the lithium plate, so it's always emitting electrons at the same time while it's being bathed in light. So first we're gonna calculate the work function of the lithium plate, and all we really have to do is convert this into joules, because that's the units that we're going to be getting with the rest of our energies here. And then we're going to calculate the energies of the two laser beams and see which one is stronger than the work function. Normally only one of them is right. So we're going to calculate the work function. Of the lithium plate. So it's so we have it at 2.93 times our conversion constant, which is 1.602 times 10 to the power of minus 19, and that's going to give us 4.69 times 10 to the power of minus 19 joules. And so we just want to find now the laser that's going to have a stronger energy than this work function here. So if we go ahead and do our calculation with the equation E equals hc over. Alright, so Planck's constant, which is 6.66 times 10 to the power minus 34. And then the speed of light, which we're just going to round up to 3 times 10 to the power of 8. In reality, it's a little bit lower than that. And then so we're just going to plug in our wavelength numbers and get the energy for each of these lasers. So we have E red equals 6.626 times 10 to the minus 34 times 3 times 10 to the power of 8 over lambda red, which is 694. Let's not forget the units, which are always in meters, so 10 to the minus 9. And then this is going to give us approximately 2.86 times 10 to the power of minus 19 joules. And then we're going to do the same thing for the violet light. So the same constants. And then a different value at the end. And then this is going to give us 4.91 times 10 to the power minus 19 joules. And then, so we can see that the energy of the violet light, the protons of the energy of the violet light are the one superior to the work function of the lithium plate. So while for the red light is inferior, so the violet light is the only one that's going to work. So this is the violet light is the laser that the spies need to use.
Okay, for the second part of the problem, you're going to want to determine the kinetic energy of the electrons that are emitted, and given the work function that you got up here. And so for this, you're going to want to use the equation for kinetic energy. Which is equal to constant times the speed of light over the wavelength minus the work function. So here you're given that we use the one that we determined that emitted the electron or the photons, which is 4.9 minus the work function that we determined. That's how you determine the kinetic energy.